Titan is Saturn's largest moon. Rivers of liquid methane carve valleys into a frozen world. Its mysterious lakes could rewrite the story of life in the cosmos. This distant, icy moon is one of the most promising places to search for alien biology. A robotic probe touched down on its strange surface, and there's the possibility of life forms that breathe hydrogen and drink methane. To discover a living world built from an entirely different chemistry, that would mean something. Our own planet started as a place of deep mystery. Billions of years back, Earth had skies of thick haze, nitrogen and methane, and young oceans that were a simmering soup of simple organic molecules. The exact chemistry that sparked life in that water is still one of science's biggest puzzles. To solve it, we need a window back in time, and that window exists, but it's hanging almost 1 billion miles away around Saturn. That's Titan. It's a frozen time capsule. It shows a landscape that looks incredibly familiar, but it's made from completely different stuff. This isn't just a vague similarity. It's a detailed blueprint of a world running on a different set of rules that might have once run our own world. The strongest parallel is the stable liquid cycle. On Earth, water evaporates, forms clouds and rains. On Titan, methane does that same dance. It flows in rivers, it gathers in big lakes and seas. It evaporates back into that thick nitrogen sky. That active cycle, even with a different liquid, is the engine. It drives geology forward, and maybe it drives chemistry forward too. Then there's Titan's atmosphere. It's like a giant probiotic lab. Sunlight and cosmic rays hit that orange haze. They break apart methane and nitrogen molecules. The pieces recombine. They form more and more complex organic compounds. Those compounds drift down to the surface like a slow cosmic snow. They coat the dunes. They rain into the methane seas. This constant, planet-wide making of life's building blocks, it's exactly the kind of process we think happened on the early Earth. So Titan's lakes are bitterly cold. They're filled with liquid natural gas, but they exist inside a system that feels hauntingly familiar. That basic similarity changes Titan. It turns it from a curious oddity into the most important comparative model in astrobiology. By studying this alien world that echoes our own, we're running a planet-scale experiment. We're testing which principles of a living world are universal, and which ones are just part of our own watery story. The first real look at Titan, we couldn't see it at all. The Voyager probes went by Saturn in the late 70s, early 80s. They took pictures, and what we got was this perfect, smooth orange ball. A hazy sphere, like a painted ping-pong ball. The cameras couldn't see through the atmosphere. It was just blank. We'd just seen Saturn's rings, all that detail, other moons with strange landscapes, and then Titan, this huge moon, the second largest one out there. It just gave us nothing, a blank stare. One scientist said it was like looking into a murky pond. You know there's something at the bottom, something maybe amazing. But you can't see it. That haze, though, that was the clue. A moon shouldn't have an atmosphere like that. It was unheard of. That thick air meant something was happening down there. It was active, it was hiding, so the very thing that blocked our view, that's what made us have to go back. Voyager turned Titan from a dot of light into a big question. It gave us proof something extraordinary was there, but no answers, just that pull. That orange veil became an invitation for a mission that wouldn't just fly by. One that would go there to stay and look and finally see through the haze. That orange stare got its answer in the summer of 2004. Cassini reached Saturn after a 7-year trip, and it went into orbit. For the people who built it, that was the moment. Decades of work. Cassini was this bus-sized machine full of instruments. but its main role was to be a carrier. It had a lander inside called Huygens. The plan was in two parts. Cassini would orbit Saturn for years, using radar to see through Titan's haze and map what was underneath. And Huygens would do something else. It would separate, drop through that thick atmosphere, and try to land on a surface no one had ever seen. It was a leap of faith, really. Huygens had to survive the heat of entry, open parachutes in an alien sky, and send its data back to Cassini, all on a dying battery. They called it the Quiet Mission. For 22 days after it let go, Huygens just drifted toward Titan, silent. Then, in January, a signal came through. It was alive. On the way down, it sampled the air, measured the wind, and a camera started taking pictures, looking down through the orange gloom. What came back changed everything. A smudge became a place. The first photos showed a pale landscape with dark, branching channels everywhere. It looked like a coastline from an airplane window. Then a soft thud. It had landed. It was sitting on a plain of dark, damp gravel with rounded chunks of water ice all around. The temperature was -290 degrees. And it was transmitting from the surface of a moon. For 90 minutes, it sent data and pictures, a view of a pebbly streambed under that hazy orange sky until the battery died. That one transmission was everything. It proved the rivers were there. It showed complex organic chemistry happening right on the ground. But Cassini was the one watching from above for 13 more years. Its radar cut through the haze, drawing coastlines, mapping mountains, and finding Titan's biggest secret. Not just rivers, large, dark pools of liquid. They had found the lakes. The radar data gave us a picture built from echoes, a world in negative. The bright parts were rough, solid ground, mountains and valleys of water ice. But then, across the poles, especially the north, you had these strange dark shapes, pitch black on the radar. They absorbed the signal completely. They were unnaturally smooth. And they had these incredibly sharp edges, like ink spilled on a map. A smooth, dark surface that reflects almost nothing back. On Earth, that means one thing. A very still body of liquid. The scientists saw it almost instantly. They were looking at shorelines. They were looking at lakes. Not just a few, but hundreds of them, clustered around the colder poles. And some of those dark patches were enormous. The biggest one, Kraken Mare, is larger than the Caspian Sea. Next to it are Ligeia Mare and Punga Mare, each one vaster than any of the Great Lakes. These aren't ponds, they're proper seas with coasts and bays and depths Cassini measured to be hundreds of feet deep. The smaller lakes told another story. They were often in depressions with steep sides and rounded shapes. Many looked like they were sitting in sinkholes, as if the ground had dissolved away beneath them. And that might be exactly what happened. On a world where the bedrock is water ice and the rain is liquid methane, the chemistry gets strange. The methane might slowly eat away at the ice, dissolving it, carving out these perfect cup-like basins that then fill with liquid. So the map showed a world with a full, working water cycle, but built from methane. The liquid gathers in polar seas and in countless little lakes. The sun's weak heat causes it to evaporate, forming clouds in that thick nitrogen sky. Those clouds drift, and eventually they rain liquid methane back down. It feeds the rivers that carve the valleys and refill the lakes. It's a complete planet-wide system. It has weather, it has erosion, it has geology, all of it powered by a liquid that, on our world, we burn for fuel. That was the revelation. Titan wasn't just a frozen rock with a weird atmosphere. It was a world with its own alien oceans, its own alien coastlines, its own active, driving rhythms. The map showed a place that felt alive in a geologic sense, whispering that the ingredients for something more might already be stirring in its depths. Titan feels familiar and alien at the same time. It has an engine. Evaporation, clouds, rain, but the liquid is methane. You have this vast, dark surface at Krakenmare. The sunlight is weak. It's not strong enough for waves. But it gives just enough energy. Molecules at the surface, methane and ethane, they gain that tiny heat. They break free. They drift up into that thick, orange sky. They rise into the cold air, dense air, and they start to condense. They form clouds, not water vapor clouds, dense, swirling banks of hydrocarbon fog. These clouds gather, they drift with the wind, and when it's right, it begins to rain. A slow, steady drizzle, liquid methane. This rain falls across the icy highlands, the dunes. It gathers into rivulets, then streams, then rivers that carve through the landscape. Cassini's radar saw these river channels everywhere, branching tributary networks. They look exactly like river systems on Earth. They flow downhill following the topography. They cut valleys into water-ice bedrock, and they empty into the lakes and seas. It completes the cycle, a full, working meteorological system. We even saw evidence of seasons. Over years, Cassini watched. Dark areas around some lakes expanded and contracted. Some shorelines seemed to change. The data suggested lake levels were rising and falling, likely from evaporation. Rainfall patterns shifting with Titan's long, slow orbit around the Sun. This active weather is the heartbeat. It means Titan is not a static, frozen sculpture. It's geologically alive. Materials are constantly on the move, eroding the high places, filling the low ones, mixing everything together. For astrobiologists, that movement is the first box to check. A potential abode for life needs an energy source. A way to exchange materials. The sun provides the faint energy, and this relentless methane cycle, the rain, the rivers, the evaporation, that's the great mixer. It churns the simple organic compounds, the ones that snow down from the atmosphere. It washes them into the lakes where they can dissolve, interact, and perhaps over immense spans of time become something much more interesting. The lakes aren't just still, cold pools. They're the endpoints of a planet-wide delivery system, collecting the very ingredients, the ones life would need to begin. 90 minutes of data from a silent world. The Huygens probe had landed. It was on this surface of damp, dark gravel under an orange twilight that never ends. For the scientists, that short transmission, it was a revelation. Titan stopped being a theoretical model in that moment. It became a place you could stand on. The descent was this slow ballet through an alien sky, 2.5 hours drifting down on parachutes, its instruments sampling the air, listening to the wind. And a single camera taking picture after picture, looking down through all that haze. The first images showed nothing, just a uniform, featureless orange. But then, as it dropped lower, shapes began to emerge. These faint, dark lines branching across a pale landscape. They were drainage channels, river networks. Carved by flowing liquid, the view was eerily familiar, like a black and white aerial photo of desert canyons. But the chemistry was all wrong. This riverbed wasn't carved by water. It was carved by liquid methane. The touchdown was soft, a gentle thud into a surface that gave way. The probe's sensors reported a consistency like wet sand. Or maybe soft clay. It had settled onto a plane of water ice grains, but these grains weren't clean. They were coated in a sticky, organic sludge. Scientists call it Tholins. That's the dark material. It gives Titan its orange color. Complex hydrocarbons created up in the atmosphere that slowly snow down. They blanket the entire world. So the ground was cold, damp with liquid methane and ethane, and covered in the building blocks of life, just sitting there. The most iconic image from the surface is a panorama. Looking out from the probe, it shows a flat plain, strewn with these rounded, smooth pebbles of water ice, stretching out to a hazy horizon. Those pebbles are crucial. Their rounded shape that doesn't come from wind. It comes from tumbling in a liquid, Likely in that very river channel Huygens saw from above. It was direct proof. Physical proof of recent fluid flow. One project scientist described the scene: profoundly still, profoundly silent, a dim, salmon-colored sky, a landscape of soft shadows, and a deep quiet. He said it felt both hauntingly familiar and utterly alien. That first-hand perspective changed everything. It grounded 13 years of orbital data, made it a tangible reality. It proved the models were right. Titan had a surface shaped by familiar processes: erosion, sedimentation, fluid flow, but executed with completely alien materials. That combination, the familiar and the strange, that's what makes Titan so compelling for the search for life. We knew then for certain the ingredients weren't just in the atmosphere. They were right there on the ground, mixed and washed by rivers, waiting in the cold. That orange haze isn't just a curtain, it's a factory, a planet-wide chemical reactor hanging there in the cold. Every day, the weak sunlight that gets to Titan, plus a steady rain of cosmic rays from space, hits the molecules in that atmosphere. They're simple molecules. Methane, that's one carbon with 4 hydrogens, and nitrogen, 2 nitrogen atoms bound up. That energy is violent. It breaks those simple bonds. It shatters the molecules into reactive fragments, atoms and pieces desperate to grab onto anything. And they do. In that frigid dark, these broken pieces collide and recombine, but they don't just go back. They form new, more complex arrangements. Benzene rings, those hexagonal foundations of so many organic compounds. Hydrogen cyanide, a molecule that's a crucial step toward amino acids, the building blocks of proteins, acetylene, ethane, a whole zoo of hydrocarbons and nitriles. This process builds upward from simple to complex in a slow, constant churn. It's a cosmic version of those experiments from the 1950s, where scientists tried to recreate the chemistry of a young Earth. But on Titan, it happens naturally, on a global scale, every single day. The products of this high-altitude chemistry, they don't stay up there, they're heavy. They condense and they start to fall. It's a slow, silent snow of organic material, drifting down through that orange sky over millions of years. It settles everywhere. Around the equator, the winds gather this dark, sand-like powder into vast dune fields. Dunes not of sand, but of frozen, complex hydrocarbons. Other places, it just coats the ground like a sticky, primordial tar. But the most intriguing destination is the lakes. When this organic snow falls into the liquid methane and ethane of Kraken Mare or Ligeia Mare, it doesn't just sit. Some of it dissolves. The lakes become more than just reservoirs of cold liquid. They become repositories of dissolved organic chemistry. Think of them not as puddles of gasoline, but as maybe the coldest, most alien probiotic soup in the solar system. All the pieces are there, constantly delivered from above, and now held in a liquid solvent. A solvent that can mix them, bring them together, let them interact. This raises a question. On Earth, we think life began when simple organic molecules, bathed in liquid water and energized by sunlight or heat, started forming more complex structures that could eventually self-replicate. Titan offers a parallel recipe, but with every ingredient swapped. The solvent is liquid methane, not water. The energy is faint sunlight and cosmic rays. But the building blocks, the complex organic molecules, are raining down in abundance. So we have to ask, could the same principles of chemical evolution work under such different rules? Could this constant, billion-year rain of organic pieces, stirred in a methane sea, ever stumble onto a reaction pathway that leads toward something we'd recognize as biology? This chemical richness, this endless production of life's raw materials, is the first pillar, the strongest argument that Titan is a world where we might find, if not life itself, then the chemistry that comes right before it. All those building blocks, that organic rain, it builds up to one question. Could anything be alive in those dark, cold seas? To even start, you have to step back from everything you think you know. Our whole idea of life is built on one example, our own. We're carbon-based, water solvent, DNA-driven. It's the only kind we've ever seen. So for decades, we've looked for planets with liquid water, calling them habitable zones. But that definition might be too narrow. We might be guilty of a bias, a cosmic bias. Titan, with its methane lakes and 300 below temperatures, forces that question. It asks us to consider life not as we know it, but as it could be. That's the realm of alternative biochemistries. The core idea is a simple swap. On Earth, water is the medium inside every cell. It dissolves nutrients, lets reactions happen. Life here is a watery phenomenon, but on Titan, water is solid ice. It's the bedrock. The liquid that flows is methane and ethane. So what if a form of life evolved to use that liquid instead? What if its internal chemistry was built to operate in a bath of liquid hydrocarbons? This isn't just fiction. Astrobiologists model these possibilities. Methane is still a solvent. It can dissolve many of the complex organics that snow down on Titan. It could let molecules move, meet, react in ways that could lead to self-organization. The implications of that swap are staggering. First, the cold. Chemical reactions slow down with temperature. Any metabolism in Titan's lakes would be achingly slow by our standards. A process that takes a second in your body might take days there, or weeks, or years. Their entire pace of existence, their perception of time, could be glacial, life cycles spanning millennia. Second, the very structure of a cell would have to be different. On Earth, our cell membranes are made of phospholipids, molecules with a water-loving head and a water-fearing tail. They form a stable bilayer in water. But that structure would fall apart in liquid methane. Researchers have proposed an alternative, a molecule called acrylonitrile, which we know is in Titan's atmosphere. It could theoretically form stable, flexible structures in methane, called azotosomes. These could act as the walls of an alien cell, containing its internal chemistry. And what would it eat? What would power it? One hypothesis looks at the atmosphere. Cassini detected a mysterious depletion, hydrogen and acetylene at the surface. These molecules should be there, but they seem to be disappearing. One possible explanation: they're being consumed. A hypothetical methane-based microbe might breathe hydrogen. Combine it with acetylene to release energy, analogous to how we breathe oxygen, a metabolism running in slow motion, fueled by the gases in that orange sky. This is why Titan is revolutionary. It isn't just another candidate for Earth-like life. It's a test case for an entirely different rulebook. To limit our search to life as we know it is to assume we have all the answers. In a universe still asking the questions, Titan forces the imagination to expand. It whispers that the most alien life might not be in warm, tropical seas, but in the silent, dark depths of a hydrocarbon lake, living a patient, cold chemistry we are only beginning to comprehend. The dark surface of a Titan lake acts as a shield. It blocks radiation from space that creates a quiet world underneath. To think about life there, you have to look at what these lakes are. They're not just methane. They're more like a complex cocktail. The main ingredient is liquid methane, but there's a lot of ethane mixed in. That mixture has different properties. It stays liquid across a wider temperature range. It can dissolve different materials, and Cassini's data suggests dissolved nitrogen might be there too. It could bubble out like fizz from a soda. Then there's the material that falls from the sky, the constant snow of organic compounds, tholins, nitriles, benzene rings. When this rain hits the lakes, some floats, some sinks, some dissolves, so the lakes aren't barren. They're a chemical soup, a reservoir of probiotic ingredients constantly restocked from above. Now the lakebed on Earth, lake bottoms are where life thrives. On Titan, the lakebed is water ice, but it might not be inert. Titan has a warm, rocky core heated by Saturn's gravity. That internal heat could drive hydrothermal activity, vents on the lake floor where warmer water-ice mixtures seep up into the cold hydrocarbon sea. That's a critical idea. It provides an energy gradient, a difference between the warm vent and the cold lake. Life could exploit that. It also brings different chemicals from the interior, mixing with the organics from above. A meeting of two worlds right there on the dark lake floor. The lake itself might be layered. Different densities of liquid hydrocarbons could create distinct zones. A methane-rich layer near the top, heavier ethane and dissolved organics settling deeper down. Each layer would have its own chemistry, its own temperature. Just as Earth's lakes have surface zones and dark midwaters, Titan's seas could offer multiple apartments in a single building. A hypothetical organism might live in the dense bottom layer, feeding on organics that rain down. Another might float between two layers, harvesting energy from chemical differences. The liquid overhead provides a stable environment. It buffers temperature swings. It shields from radiation. It's a haven. So when we ask if Titan's lakes are habitable, we're not asking about a uniform puddle. We're considering a dynamic, layered environment. One that connects the atmosphere's factory to the moon's internal warmth. It offers a spectrum of potential niches, a place where an alien metabolism could find a home, not in spite of the cold and darkness, but because of the unique chemistry those conditions create. The lake is more than a feature. It's a world within a world, holding its secrets in a deep, liquid silence. The lakes are one part of it, but there's another part, and you have to look underneath. Beneath the ice crust, beneath all the rivers and dunes, there's a hidden ocean, but it's not methane. It's water, liquid water, and this isn't just an idea. We got proof from Cassini in its final years. The way the spacecraft measured Titan's gravity and the slight wobble in its orbit around Saturn, it told a clear story. The surface, that hard shell of water ice, isn't attached to the core. It can move on its own, it can shift, and the only way that happens is if there's a global layer of something slippery in between. A subsurface ocean, a huge, dark sea trapped between a frozen ceiling above and a rocky floor below, probably kept liquid by ammonia acting like antifreeze and by Saturn's gravity constantly squeezing it. That changes everything. It means Titan isn't just a world with lakes on the surface. It's an ocean world like Europa or Enceladus, but with an extra layer. An extra level of complexity, so you have to picture this hidden place. No sunlight ever gets there. The pressure is enormous. The temperature, while above freezing, is still near freezing. It's a realm of total darkness, total silence, but for astrobiologists, that's a deeply exciting environment, because this ocean is water. It's a habitat we understand. On Earth, we find life in the darkest, coldest, highest pressure parts of our oceans, around hydrothermal vents. The same idea could work here. Tidal heating from Saturn could drive hydrothermal activity on that rocky seafloor, providing chemical energy. Providing nutrients, life as we know it could potentially exist down there, completely cut off from the strange surface world above, and that opens up a staggering possibility. Titan could be a world with two separate places where life might exist. On the surface, a cold, hydrocarbon-based biosphere, breathing hydrogen, drinking methane. And deep below, in the buried ocean, a warmer, water-based biosphere, maybe fueled by chemical vents, two potential biospheres, built on completely different chemistries. Existing on the same world, but probably never interacting. The surface is too cold, the ice shell is too thick, there's no real exchange. They'd be parallel stories of life. Written in different languages, on different pages of the same book. That kind of duality, it's unmatched in our solar system. It makes Titan not just one candidate for alien life, but two. A double mystery wrapped in an icy shell, shrouded in that orange haze. You need a connection between them, a way for that deep ocean to reach the strange surface. There's a possible mechanism for that. It's called cryovolcanism, not volcanoes of fire, but volcanoes of ice, erupting a cold, slushy mix of water and ammonia. On Titan, the evidence is intriguing. Cassini saw features that don't look like craters or old mountains. One region is called Sotra Patera. There's a deep pit there, over a mile deep. Right next to a tall mountain named Doom Mons. The whole area looks like a volcanic field, but made of ice. The mountain could be a dome built up by eruptions. The pit might be a collapsed caldera. It's a landscape that feels geologically alive. This process could be the link. Think about that subsurface ocean. It's under pressure against a warm, rocky core. In some places, that warm, ammonia-laced water might find a crack in the ice shell above. It forces its way up. It erupts as a slow, creeping flow of icy mud. It freezes into new landscapes, but it brings two things with it: heat and chemistry. The heat from this slurry, while still incredibly cold, is a real energy source on a world that's minus 290 degrees. That temperature difference creates a gradient. It can drive reactions. More importantly, it transports materials. The ocean isn't just water. It has salts, minerals, compounds from the rocky core. A cryovolcano delivers these to the surface. It brings deep ocean materials, potential nutrients, right into the domain of the surface organics. It mixes the ingredients from the wet interior with the hydrocarbons from the sky. So the surface lakes aren't just collecting from the atmosphere. They might get periodic infusions from the warm depths below. This activity paints Titan differently. Not a static frozen ball, but a world with a layered engine. Powered by Saturn's tides, internal heat, the chemical factory in its sky. Cryovolcanism suggests a world that's actively renewing itself, creating new surfaces and shuffling the deck between its two habitable environments. It turns Titan from interesting features into an integrated system. A system where the search for life isn't confined to one layer. It might be a story written in the slow exchange between the hidden ocean and the alien lakes. Titan's seasons move slowly. They last for decades. It takes this moon 29.5 years to orbit the sun, so each pole gets a very long winter. Almost 7.5 years of continuous darkness, then a long, gradual summer. Cassini was there long enough to see part of that cycle, and it saw a world responding to the sun. The clouds showed it. During the northern winter, the North Pole had a dense hood of hydrocarbon clouds. As spring approached, that hood started to fade. But then, over the equator, huge methane storm clouds gathered. They saw the surface darken after those storms, like a methane rain had fallen on the dry dunes. That was a surprise. Rain at the equator, like a monsoon in a desert. It meant the climate was more active than anyone thought. The lakes were changing too. Over years, radar saw shorelines shift. The dark surfaces expanded and contracted. The likely cause is evaporation and rain. In the long polar summer, weak sunlight makes methane evaporate from the lakes. It goes into the air, forms clouds, and winds can carry it. It might fall as rain somewhere else, even at the equator. Then in the long winter, evaporation slows. The lakes might refill from rain or from underground, so there's a rhythm, a pulse of wet and dry. That pulse could span generations for any life on the surface. For something living in a Titan lake, these decades-long seasons would be its whole world. A long summer might be a time of plenty, evaporation and mixing, bringing in new organics. But as winter comes, the lake level drops. Maybe it freezes at the edges. It could become a time of scarcity. Life would need to adapt. It might hibernate, lie dormant in the cold sediment for years, until the next warm pulse, or it might migrate, follow the shoreline back, move to deeper, more stable parts of the sea. This seasonal change adds something to the idea of habitability. A place isn't just habitable or not. Its hospitality might come in waves, windows that open for a decade, then slowly close. For biology, that pulse could be a driver, a reason to become resilient, a clock set to the turning of a planet and a distant sun. It means on Titan, time is a key ingredient. And patience is part of the story. The lakes collect the rain, but at the equator, it's different. You have these huge deserts, but they're not sand, not like ours. These are Titan's dunes, massive linear ridges, some as high as skyscrapers, stretching for hundreds of miles over the frozen ground. From orbit, they look like the dunes of Namibia. But the material is alien. This sand isn't silicate rock. It's a dark, organic powder. The constant snow from that orange sky, the complex hydrocarbons, benzene and other compounds, it all settles here. And the winds, driven by Titan's slow spin and its thick atmosphere, they gather this material and shape it into these monumental waves. They aren't static. Cassini watched them move over the years. It's a dynamic, shifting landscape, but one made from the very building blocks of life, ground into fine grains. You can think of these dune fields as a bank, a planetary-scale repository of organic material. All that complex chemistry made in the high atmosphere doesn't just disappear. A lot of it ends up here, stored in these towering, dark piles. It shows the output of Titan's chemical factory. This process has been running for billions of years. The dunes are an almost unimaginable stockpile of probiotic compounds, just sitting there, waiting. That leads to a thought, a speculative one. We look at the lakes as a potential habitat where organics dissolve in liquid. But what about these dry, organic grains themselves? Could they ever be more than inert sand? Under the right conditions, maybe. If a methane rain shower dampened these dunes, even briefly, that would create a temporary solvent. Or a cryovolcanic flow oozing across the desert. That would bring heat, water ice, and minerals from deep inside into contact with this huge organic reservoir. Suddenly you have moisture, energy, and a rich supply of carbon-based molecules all in one place. It's a recipe for accelerated chemistry. The dunes themselves are probably too dry and exposed for any long-term biology. But they aren't irrelevant. They are the raw material supply. A library of organic molecules cycled by the wind, available to be moved, maybe by rare floods or winds, to places where liquid and energy could spark something new. So the dunes are more than a beautiful feature. They are a measure of Titan's potential, a silent record of all the chemical reactions that have happened in its sky, now lying in deep, dark piles. Holding a story that hasn't been read yet. That orange veil is a real barrier. It stops most light, but it's not a perfect one. To see the surface, you can't use the light our eyes see. That light just gets lost in the haze, so you have to look with different eyes. You look in the infrared. In the infrared, light behaves differently. Methane, the gas that blocks visible light, it becomes transparent, but only at certain specific wavelengths. It's like a stained glass window. Most of it is dark, opaque. But there are a few clear panes, a few spots where you can see through. Scientists call these atmospheric windows, and through these narrow windows in the infrared, you can finally look down. You can see Titan's hidden landscape. The Cassini spacecraft had an instrument for this, the Visual and Infrared Mapping Spectrometer, VIMS. It didn't take normal color pictures. Instead, it collected the faint infrared light from the surface. It split that light into hundreds of individual wavelengths, and every material on Titan, water ice, frozen carbon dioxide, organic gunk, each one absorbs and reflects infrared light in a unique way. Like a chemical fingerprint, by reading these spectral fingerprints, VIMS could map what the surface was made of, not just what it looked like. The data showed a world of real chemical diversity. The bright, rugged highlands had the clear signature of water ice. That's Titan's bedrock, but in the dark, low areas, especially near the lakes and seas, the signature changed. There, the ice was contaminated, coated with dark organic compounds that fall from the sky. The dunes around the equator had their own distinct fingerprint. It matched the complex hydrocarbons scientists had predicted. VIMS even found places with deposits of frozen carbon dioxide and benzene, evidence of active chemistry happening on the ground. This remote chemical mapping is a quiet triumph. It lets scientists do geology from 1 billion miles away. They could see which regions collected the most organics, which areas had been washed by methane rain, which ancient terrains might hold a record of Titan's past. It turned a blurry orange ball into a detailed laboratory map. It highlighted the benches where the experiments were running, where probiotic chemistry was most active. This global guidebook, written in infrared light, tells us where to look next. It focuses the search on the places where the ingredients are most richly mixed. That chemical factory in the sky runs on methane, and sunlight is always breaking it apart, using it up to make all that complex organic snow. The math is simple. That process should have used up all the methane in Titan's atmosphere a long time ago. Maybe within 50 million years, but Titan is ancient. It's over 4 billion years old, and its air is still 5% methane. So where is it all coming from? That's the methane mystery, and the answer probably means Titan has a hidden, active heart. The first main theory is about a deep reservoir. It's not just about the surface lakes. It's about a planet-wide plumbing system. Beneath the icy crust, there could be a huge layer of liquid methane, mixed with ethane and nitrogen, a global aquifer of natural gas trapped in porous ice or between layers. This is separate from the subsurface water ocean. It's a shallower layer of liquid hydrocarbons, and geological activity could force this liquid to the surface. A shift in the ice, the pressure from Saturn's tides, it could outgas through cracks or erupt in cryovolcanic events, releasing fresh methane vapor directly into the air. It would be a slow-release valve, topping up the fuel tank as sunlight burns through it. The second theory is more intriguing. It suggests planetary recycling. The methane might not just come from below, it might be remade on the surface. All that ethane produced in the atmosphere rains down and fills the lakes. But that might not be the end. On the floor of those dark seas, in contact with water ice bedrock and maybe internal heat, complex geochemistry could be working. Catalytic reactions, maybe with minerals from the core, could convert ethane back into methane, a process called hydrogenolysis, so the lake bottoms could be giant cold refineries. Taking the waste product and turning it back into the starting fuel, that methane would then bubble up through the lakes, re-entering the atmosphere to start the cycle again. Both ideas point to the same thing. Titan isn't a passive world where chemistry happens and stops. It's a dynamic, integrated system, cycles within cycles. A great chemical loop that preserves its most volatile ingredient for billions of years. This active recycling is the kind of process that maintains stable, long-term conditions. And stability is key for the slow, patient work of probiotic chemistry. A world that can regulate its own atmosphere, that can replenish its essential compounds, is a world that provides a consistent stage. For experiments in complexity to run across geologic time, the methane isn't just a gas. It's the signature of a living world, not biologically but geologically. A world that is still writing its own story. We can't see these cycles happen in real time, so we have to bring a piece of Titan to Earth into a lab. They build a miniature version of that world, start with a simple setup, a cold chamber, a steel cylinder filled with the basic gases from Titan's atmosphere, nitrogen and methane. They chill it down to that extreme cold, -290 degrees. Then they add the spark, a source of energy like the sunlight and cosmic rays hitting Titan's haze. Sometimes it's a beam of ultraviolet light, other times it's an electrical discharge, a tiny, contained lightning storm in a bottle, and then they wait. The process is slow. Over hours or days, a change begins. A faint, reddish-brown stain appears on the cold walls. It thickens, it becomes a sticky, tar-like coating. That material has a name, Tholins. It's a catch-all term for the complex organic polymers you get when you zap simple gases with energy. It's the very stuff that gives Titan its orange glow. In these labs, Tholins aren't just a curiosity. They're a Rosetta Stone. By creating them here under controlled conditions, scientists can analyze them with every instrument we have. They can break them apart molecule by molecule to see what's inside. The results are a direct match. The complex hydrocarbons, the nitriles, the benzene rings, all the spectral fingerprints that Cassini and Huygens detected from 1 billion miles away, we can make them on a lab bench. This is our ground truth. It validates the remote observations. It tells us our models of Titan's high atmosphere chemistry are correct. But these experiments do more than confirm. They predict. By tweaking the gas mixtures, the energy sources, the pressure, researchers can simulate different parts of Titan. What happens over the cold lakes versus the warm equator? What chemistry might occur if a cryovolcano spews water ice into a hydrocarbon pond? They can trace the pathways. They can watch, step by tiny step, as a simple molecule of methane is transformed through a series of reactions into a precursor for an amino acid. These labs are where we run the experiment of Titan's potential in fast forward. They let us ask, if we let this process run for 1 million years in this bottle, what would we get? Could these Tholins, given the right solvent and enough time, begin to self-assemble into more ordered structures? The sticky, reddish gunk coating the inside of a glass chamber is a tangible piece of an alien world. It's physical evidence that the processes we imagine are not just possible, they are inevitable given the conditions, and it holds within its complex, messy chemistry the faintest outline of a path. A path that, on a world with lakes and time, might lead somewhere extraordinary. The next part of this story is already built. It has wings. In 2028, if everything goes to plan, a spacecraft will start a long trip back to Saturn's largest moon. Its name is Dragonfly, and it's different from anything we've sent before. This isn't an orbiter, it's not a static lander. Dragonfly is a Rotorcraft, a nuclear-powered drone built to fly through the thick, calm air of Titan. Think of it as a large, sophisticated quadcopter, but with 8 rotors stacked in pairs. It will land near the equator at a promising site, and then it will take off again. It will fly for miles, land somewhere new, sample the ground, and then fly once more. Over a planned mission of almost 3 Earth years, Dragonfly could travel to dozens of different locations, from organic dunes to the floor of an ancient impact crater. That mobility changes everything. For the first time, we won't be limited to a single snapshot from one place like Huygens gave us. We'll get a survey, a guided tour across an alien world. The mission's target is a region of major geological interest near the Selk impact crater. An impact is a violent event. It's energetic. It melts the ice bedrock. For a brief time, it creates a pool of liquid water on the surface, even on freezing Titan. That liquid water would have mixed violently with the complex organic compounds coating the ground. It's the perfect laboratory setup. Water, organics, and energy all brought together. That surface water would have frozen solid again long ago, but the chemical products of that ancient meeting could still be preserved in the ice. Frozen in time, Dragonfly will land near Selk, and its flights will take it to explore this altered terrain. It carries a full suite of instruments, a miniature chemistry lab. It can drill into the surface, collect samples of the icy sand and organic material, and analyze them right there. it will look for specific molecular patterns. Complex arrangements that could hint at probiotic chemistry advancing toward biology. One project scientist described Dragonfly's goal with clear excitement. We are going to Titan to directly measure, for the first time, how far probiotic chemistry has progressed in a natural laboratory that has been operating for billions of years. We are not going with the explicit goal of finding life. We are going to find the chemical signatures that life, if it exists, would leave behind, the biosignatures of a potential methane-based biology. This is the revolutionary step, moving from watching from orbit to touching down in multiple places, to tasting the very stuff of that alien world. Dragonfly turns Titan from a distant object of study into a place we can truly explore. Mile by mile, flight by flight, bringing its deepest chemical secrets into the light, Dragonfly is looking for clues, just not the kind you might think. On a world like Titan, you can't look for the usual signs. There won't be any green forests to see from space, no atmosphere full of oxygen to detect from a distance. The search here is for something much more subtle. It's a hunt for chemical whispers. Scientists call these biosignatures. A biosignature is any substance or pattern or phenomenon that gives you evidence of life. Past or present on Earth, that's the oxygen in our air that comes from photosynthesis or a specific molecule like chlorophyll that's only in plants. But on Titan, with its different chemistry, the biosignatures would be totally alien. The search becomes forensic. You're looking for evidence of a process that shouldn't happen unless a living system is driving it. The first big clue might be in the air. Cassini's data gave us a hint. The spacecraft measured gas concentrations down to the surface. Two gases, hydrogen and acetylene, showed a strange pattern. They were present higher up, but they seemed to disappear near the ground. That was puzzling. These molecules should be stable. They should be raining down onto the surface from the atmosphere above. One explanation could be simple chemistry. They might be reacting with something on the ground. But another possibility, a more exciting one, is that something is consuming them. A hypothetical form of life on Titan might use hydrogen like we use oxygen. It could breathe it, combining hydrogen with acetylene in a slow, cold metabolism to get energy. If Dragonfly lands and confirms this depletion is real, and finds it's focused in areas rich in organics, that's a powerful clue, not definitive but powerful. It would point to an active process that looks like consumption. The second set of clues is in the dirt. Dragonfly will scoop up samples of Titan's sand and ice, which are full of organics. Its onboard lab will analyze the molecular structures inside. Life, even alien life, isn't random. It's selective, it's efficient. It tends to build molecules with a specific handedness. Chirality. Most non-biological processes make a roughly equal mix of left-handed and right-handed versions of a molecule. Biology, though, often prefers one type exclusively. Like using only right-handed screws to build a machine, if Dragonfly finds a strong, consistent preference for one chiral form in certain complex organics, that's a huge red flag. And then, life often works with lighter isotopes of elements. It prefers carbon-12 over the slightly heavier carbon-13. That preference leaves a fingerprint in the ratios. A pronounced skew in these ratios in Titan's materials could signal biological processing. The immense challenge is the noise. Titan's entire environment is a roaring engine of complex, non-biological chemistry. Distinguishing a biological signal from that background noise is maybe the hardest problem in astrobiology. It requires extreme precision. It requires understanding every possible non-living pathway first. This is why Dragonfly is mobile. It has to move from place to place, comparing a dune field to a lakebed to an impact crater. It needs to see if these potential biosignatures are concentrated in specific, distinct locations, like life would be, or if they're scattered uniformly by geology and weather. The mission turns the moon into a vast crime scene. The Rotorcraft becomes a detective, gathering chemical evidence from every corner, piecing together a story written in atoms and isotopes. It's a meticulous, patient search for a pattern within the chaos, a pattern that says this wasn't just chemistry, this was something more. Looking for these chemical traces, it comes with a real weight. We're contacting a place that could have its own quiet kind of life, and that brings up a hard question. How do you investigate a place like that without accidentally ruining what you went there to see? That's where planetary protection comes in. It's a set of rules, a kind of philosophy for going into space. The heart of it is straightforward to say, but really difficult to do. You have to stop forward contamination, which means making sure our machines don't carry Earth microbes to another world. A single tough bacterium from here, catching a ride on Dragonfly, might live through the trip. If it got into Titan's environment, it could grow. It could spread in ways we can't foresee. And then if we ever saw signs of life on Titan, we'd have a huge problem. Did we find alien life, or did we just find our own contamination? The whole point of the mission would fall apart. So to stop that, Dragonfly is being built in some of the cleanest rooms we have. Its parts are baked at high heat. They're washed with sterilizing chemicals. Every bolt, every circuit, every piece of the Rotorcraft is handled with one goal: to send a machine to Titan that's as biologically clean as we can possibly make it. This isn't just about being clean. It's about protecting the integrity of an experiment that's been running for 1 billion years. Titan's chemistry has been working in isolation. Putting a new thing in, an Earth microbe, would be like dropping a modern computer into an ancient workshop. You couldn't trust anything you saw after that. Then there's the other side, backward contamination. That matters more for missions later on that might bring samples back. If we ever get material from Titan's surface or its underground ocean, we'd need to be completely sure it holds no biological danger. The odds are incredibly small, but the care has to be total. Any sample that came back would be held under the strictest containment, studied in secure labs before anything was released. These rules change the mission. Dragonfly isn't just a robot explorer, it's a steward. Its design recognizes something sobering. We're going into an alien setting not as conquerors, but as careful visitors. Our tools have to be spotless so that our questions stay clean. All this work to sterilize the spacecraft, it's a quiet proof of how serious the search is. It's a physical way of showing respect for what we don't know. It says we care enough about the answer to make sure our own fingerprints aren't all over the evidence. This ethical layer turns the trip from just exploration into something like cosmic diplomacy. We're hoping for an introduction, but we have to knock very, very softly. The story of Titan isn't alone. It's part of a whole group of worlds in our solar system, places with oceans hidden inside. To really see it, you have to look at the others. The best examples are around Jupiter and Saturn. There's Europa, a moon of Jupiter. It has this smooth, cracked shell of ice, and underneath, the evidence says there's a global ocean of salt water. Maybe twice as much water as all of Earth's oceans. Then there's its neighbor, Ganymede, even bigger. It probably has an ocean that's layered, sandwiched between different kinds of ice. And then Enceladus, this small, bright moon of Saturn. The Cassini spacecraft flew through plumes coming from its south pole. Water vapor, ice crystals. It tasted salts, it tasted organic molecules. These are the classic ocean worlds. Their potential for life comes down to one powerful idea: a liquid water ocean sitting right against a rocky seafloor. That contact is everything. Water reacts with rock, it pulls out minerals, it can drive chemical reactions. On Earth, that exact process supports whole ecosystems. At the deep sea vents, life with no sunlight at all, so the search on these moons is straightforward. Find the water, then look for the chemistry where the water meets the rock. Now you put Titan on that same table, and the whole comparison shifts. Titan also has strong evidence for a subsurface ocean, a water ocean trapped under a thick shell of ice. In that way, it's like Europa or Ganymede, but that's where the similarity ends, because Titan has something they don't have: stable liquids on its surface. Not water, lakes and seas of methane and ethane, and it's wrapped in that thick atmosphere, mostly nitrogen, a chemical factory, making complex organics that rain down everywhere. So Titan presents two potential habitats, stacked on top of each other. The familiar one, a deep, dark water ocean maybe touching rock, and the alien one, a surface world of liquid hydrocarbons interacting with that organic haze. It's the only world we know that gives you both in one package. This duality changes the investigation. For the watery moons, the search is focused. Get through the ice, sample the ocean, look for signs of that water-rock chemistry and the life it might support. For Titan, the search is doubled and the questions are different. On the surface, you have to ask if life can be built with a different solvent, a different metabolism. In the bitter cold, below, you ask the same water-based questions you have for Europa. That makes Titan a bridge. It connects the search for life as we know it in watery depths with the search for life as we don't in alien seas under an orange sky. The solar system isn't giving us one path anymore. It's showing us a branching tree of possibilities. Each ocean world is a different experiment, running in isolation for billions of years. By comparing them, you learn what's common, what's rare. You learn a world doesn't need to look like Earth to be alive, geologically or biologically. Titan stands right at that crossroads, a world of two natures, suggesting the universe's recipe for life might have more than one page. That search for a pattern, for a sign of something more, it leads you to a much larger silence. The universe is so immense and it's so old, with all those billions of stars and probably even more planets. The numbers alone suggest life should have come up many times. So where is everybody? That's the Fermi paradox. It's this contradiction, the high probability of life out there, and then the complete lack of any evidence for it. We've been searching for decades, listening for radio signals, looking for signs of huge engineering projects, and we've heard nothing, just cosmic static. One answer to that silence, it's a humbling one. Maybe life isn't the rare thing. Maybe it starts pretty easily given the right conditions, but the jump from simple life to an intelligent, technological civilization like ours, that might be the real cosmic fluke. The universe could be a quiet garden, filled with worlds where life never gets past microbes, or algae, or something even stranger and slower, and this is where a place like Titan gives you a new way to see it. If life exists there in those cold, dark lakes, it would almost certainly be simple, a patient kind of life, based on chemistry, breathing hydrogen, living off acetylene. An existence measured in millennia, it would be perfectly adapted to that niche, with no reason to ever develop a complex brain, or tools, or technology. It wouldn't build cities, it wouldn't invent radio, it wouldn't look up at the stars and wonder. It would just be, and if that kind of life is possible on Titan, then worlds like Titan might be common. All across the galaxy, frozen moons around gas giants with subsurface oceans and organic surfaces, they could be far more numerous than Earth-like planets. The galaxy might be full of these quiet, dark biospheres, each one a testament to life's adaptability and also to its limits. We've been searching the cosmos for a reflection of ourselves. For beings who would talk like we do, but we might have been looking for the wrong thing. The answer to where is everybody could be that they are everywhere. Just in forms we're only starting to learn how to see. They're in the deep oceans under ice. They're in the methane lakes under orange skies, living slow, silent lives that leave no technological signature for our telescopes to find. So Titan becomes more than just an interesting world. It becomes a model, a potential cosmic norm, a benchmark for a universe that's biologically rich but technologically quiet. Exploring it teaches you to broaden what you call a living world. It humbles the search. It suggests that the grand, communicative civilizations we imagine might be the rare exceptions. While the true story of life out there might be written in the slow, cold chemistry of countless hidden seas, long before we ever saw Titan, it was already in our stories. For a long time, it was just a blank spot, an orange dot, and writers looked at it and saw a destination, a new frontier. In Arthur C. Clarke's Imperial Earth, Titan is a human colony. A place of stark beauty. Stephen Baxter's stories made it a world of deep mystery, where explorers face environments that challenge everything. These fictional versions were places we could conquer, or at least understand. They were built from our own hopes, our own fears about what's out there. But then reality showed up, and it didn't follow the script. The real Titan from Cassini and Huygens didn't just fulfill those old dreams. It went past them. It was more nuanced, more chemically rich, more hauntingly beautiful than most stories even tried to be. Fiction imagined colonies on a kind of Earth-like rock. Science found hydrocarbon dunes, methane monsoons, the potential for a biology built from a completely different blueprint. The truth wasn't a lesser version of the fantasy. It was stranger, more compelling. The lakes were real, but they were filled with liquid natural gas. The atmosphere was thick, but it was a factory for the building blocks of life. This real Titan offered something more powerful than a simple colonization story. It presented a profound scientific question written across an alien landscape. And this back and forth between science and storytelling, it's a kind of engine. Science fiction doesn't predict the future, it prepares the mind for it. By filling Titan with ideas, with possibilities, it created a cultural familiarity, a sense of wonder. It made the public care about going there. It made the scientists they fund care. Those early stories, even when the details were wrong, framed Titan as a place worth the journey. They inspired the engineers who built Cassini, the researchers who designed Dragonfly. They turned a distant point of light into a place in the imagination, long before it became a place of data. Now the data returns the favor. Every new radar image, every chemical analysis, it feeds back into the imagination. It seeds new stories, new questions, new dreams. It's a cycle. The fiction sparks the curiosity that drives the science, and the science reveals wonders strange enough to inspire the next generation of fiction. And the next generation of explorers who will turn those imagined wonders into the next scientific targets. That orange shroud over Titan isn't just a veil. It's the Moon's most active organ, a planet-wide chemical reactor hanging in the cold sky. The stuff that makes it we call Tholins, and that's not one molecule. It's a catch-all term for a whole messy family of complex organic polymers. Like a cosmic soot, a primordial tar, it forms when simple gases get zapped with energy. On Titan, it starts up in the upper atmosphere. Sunlight and cosmic rays smash into methane and nitrogen molecules, shatter them into reactive fragments. And those fragments collide in the frigid dark. They stick together, form larger structures, more complex ones, rings of carbon, chains of hydrocarbons laced with nitrogen. They grow until they become these reddish-brown particles, floating high above the surface, and there they do two vital things. First, they're a planetary sunscreen. That thick haze absorbs and scatters the sun's harsh ultraviolet, acts as a global filter. By the time light reaches Titan's surface, it's softened to a dim, reddish twilight. That shielding is profound. It creates a gentler environment at ground level, protects any delicate chemistry happening in the lakes or on the dunes from being torn apart by the same energetic rays that help make the haze up above. The process that builds these complex organics also makes the shield that lets them accumulate safely below. Second, the haze is a constant provider. These Tholin particles don't stay aloft forever. They're heavy, they condense, and they begin a slow, silent drift downward, a perpetual, global drizzle of organic material. A rain of potential. This isn't rare. It's been happening for billions of years. Every square inch of Titan's surface has been coated, over and over, by this sticky, complex snow. It paints the dunes dark, stains the icy highlands, and most crucially, it falls right into the methane lakes and seas. There, some of it dissolves, turns those dark pools into repositories of probiotic soup. The lakes become mixing bowls where the building blocks from the sky can interact in a liquid solvent. So this iconic orange haze is the engine of Titan's surface potential. Both protector and provider, it safeguards the stage while steadily delivering the raw materials onto it. Without this global shroud, Titan's surface would be a far more hostile, irradiated place. The rich organics would be destroyed almost as fast as they formed. The haze creates the stable, enriched conditions where the long, slow experiment of chemical complexity can run. It turns the entire moon into a laboratory with a roof, where the walls themselves are constantly manufacturing the ingredients for the experiment below. Even Titan's scars show change. The surface, these plains, these dunes, it doesn't have many craters. You look at a dead world like the moon and it's covered in them. Billions of years of impacts, but Titan is mostly smooth. That scarcity is the clue. Something is erasing those wounds. Weather is doing it. Geology. The methane rain, the rivers, maybe ice creeping, cryovolcanic flows. It all acts like a slow sandpaper, wearing down the rims, filling the bowls over millions of years. So the few large craters left, like Menova, like Sinlap, they're special. They're time capsules, windows into a deeper past, into the layers below. When an asteroid hits Titan, it doesn't just make a hole. It excavates, it blasts through that dark organic blanket that coats everything, throws that material aside, and what's exposed in the crater floor, the walls. Pure water ice, Titan's bedrock. Cassini's spectrometers saw it. In those fresh scars, the chemical fingerprint changed. The dark hydrocarbon signature was gone, replaced by the bright, clean signature of water ice, a direct glimpse under the hood, proof that beneath all the alien chemistry, Titan is fundamentally a world of frozen water. These craters are like natural drill sites, showing us the foundation this whole strange experiment is built on. But the story gets more interesting right after impact. That collision is violent. It releases a tremendous burst of energy. For a short time, in and around the crater, temperatures soar. The local water ice doesn't just break. It melts for days, maybe weeks. You have a pool of liquid water sitting on Titan's surface. In that pool, something extraordinary happens. The impact also scatters the surrounding organic rich material right into this new, warm pond. Suddenly, all the key ingredients for probiotic chemistry are brought together with a jolt. Liquid water, complex organic molecules, and abundant energy from the impact heat. It's the classic recipe for the origin of life, as we understand it on Earth, but created in a flash on an alien moon. These impact sites become temporary oases. Brief, violent laboratories where chemistry can race forward at a pace unimaginable in the slow, cold methane lakes. Reactions that would take millennia in the negative 300-degree seas might happen in hours here. Could amino acids form? Could more complex chains assemble? It's a tantalizing possibility. Of course, the oasis doesn't last. Titan's deep cold reasserts itself. The water pool freezes solid, locking any new chemical products inside a tomb of ice, but they are preserved, a snapshot of a moment of rapid chemical evolution. So these rare craters are more than geological features. They are records of catastrophe that might also be crucibles of creation. They show us the moon's icy skeleton. And they hint at fleeting opportunities scattered across Titan's history, where the conditions for life as we know it briefly flared into existence, only to be captured in a deep freeze. It adds another layer to the search. Dragonfly is heading to Selk crater for this reason, to land near one of these frozen time capsules to taste the ice, hoping to find the chemical echoes of that ancient, violent, warm moment. The liquid on Titan is hard to even picture. You have to measure it against everything we have on Earth. The numbers from Cassini, from all that radar, they're just staggering. The total amount of methane and ethane in those polar seas and all the lakes, it's immense. It's hundreds of times more than all the oil and gas we've ever found here. All of it, every reserve, every field, every shale formation. Multiply that by several hundred. That's what's just sitting there on the surface of one moon. A hydrocarbon endowment on a planetary scale, and that creates this deep irony. There, the thing we treat as a precious fuel, it's the most common liquid. It's the rain, it's the river, it's the ocean, and the thing we see as essential for life, water, that's completely locked away. On Titan's surface, water isn't a liquid. It's the bedrock, it's the mountain, it's the permafrost. Water is just rock-hard ice, a permanent geology. The two have completely swapped roles. What's fluid and cyclical on one world is solid and static on the other. And this staggering volume of methane, it's the engine of the whole system. It's not a static pool. It's the working fluid for a global machine. To have a stable methane cycle that's billions of years old, you need an enormous reservoir. A buffer, the seas, Kraken and Ligeia, they provide that. They hold enough to feed evaporation for eons, to supply the rivers, to weather the long polar seasons. That scale guarantees stability, and stability over geologic time that allows for patience. It lets the slow, incremental steps of chemical complexity happen without the solvent just drying up. These lakes aren't just puddles, they're continents of potential, where organics from the sky can mix and interact in volumes that dwarf any lab we could ever build. That sheer abundance leads to a practical thought, a speculative one. For any future human presence that far out, such a ready source of fuel and chemical feedstocks would change everything. It raises questions about resource use, but that's for a much later time. For scientists now, the significance isn't industrial, it's foundational. This vast liquid inventory means the probiotic experiment on Titan isn't happening in a test tube. It's happening in an ocean. The scale itself becomes part of the argument. In a universe where chance matters, more trials increase the odds. A single small pond might never find the right combination. But a sea larger than continents, refilled by rivers and atmospheric chemistry for billions of years, that's a different kind of experiment, one where the numbers of chance tilt toward possibility. The liquid is the stage, and its sheer size suggests the play being performed on it could be epic. That huge ocean on the surface, it has to have something matching it deep down. To keep a world geologically active for that long, you need a steady energy source. For Titan, that power isn't from the sun, it's from something much closer. Titan's heat comes from Saturn. It's from a gravitational dance, this constant pull that warms it from the inside. It comes down to Titan's orbit. It's not a perfect circle. It's a bit stretched out, so Titan's distance from Saturn is always changing. When it swings in closer, Saturn's gravity pulls harder on the near side than the far side. That stretches Titan just a little. Then, when it swings back out, the pull relaxes and the moon settles. This stretching and squeezing happens every orbit. That's tidal flexing, and that constant flexing creates friction inside Titan, in its layers of rock and ice. Friction makes heat. It's like rubbing your hands together, but on a planetary scale, driven by a gas giant's gravity. This is a cosmic engine. It gives a steady, reliable internal warmth that's probably lasted Titan's whole life. It doesn't depend on a radioactive core cooling off. It doesn't fade. As long as Titan keeps that stretched orbit and Saturn keeps pulling, the engine runs. This tidal heating is what stops Titan's subsurface ocean from freezing solid. The heat comes up from the rocky core through that global water layer and helps keep it a liquid sea. It's also probably what drives the moon's geology. That internal warmth needs a way out. It can soften the ice shell above, create plumes of warmer material, fuel cryovolcanos that might reshape the surface. It's the energy that could power hydrothermal systems on the ocean floor, mixing minerals, creating chemical gradients, potential fuel for life. We see this dramatic effect somewhere else. Jupiter's moon Io is the classic case. Tidal forces from Jupiter are so strong they melt rock inside Io, making it the most volcanically active thing we know. Titan's version is much gentler but just as profound. Its heat is a slow, steady simmer, not a violent boil. It's enough to maintain a liquid ocean and some surface activity, but not so much it tears the moon apart or strips its atmosphere. It's a perfect, sustained balance. This changes how we see Titan, from a frozen picture to a dynamic system. Its potential for habitability isn't a static condition. It's a direct result of celestial mechanics. The moon's path around its planet, the shape of that path, these aren't just orbital details. They're the master switches for the internal heat that keeps the world alive. It means Titan's story, the persistence of its lakes, the possibility of its ocean, the chance for chemistry to advance, is written in that silent, relentless pull between a moon and its giant. The air on Titan is mostly nitrogen, 95%. That's the same gas that makes up most of our own air. That's not just a coincidence. Nitrogen is stable. It doesn't react much. It creates a calm background, a stage for other chemistry to happen. But where did it all come from? The main idea goes back to when Titan was forming. It probably had a lot of ammonia ice. Ammonia is nitrogen and hydrogen. In that early, active world, the ammonia could have broken apart. The hydrogen, being light, would have escaped into space. The heavier nitrogen would have stayed, held by Titan's gravity. Over a very long time, it built up this thick blanket. This atmosphere is substantial. The pressure on the surface is about 1.5 times Earth sea level pressure. You wouldn't need a pressure suit. You'd need a way to breathe and a very warm coat. That pressure is the second key. It lets liquids exist on the surface. Titan is incredibly cold, around -290 degrees Fahrenheit. At that cold, methane and ethane should just boil away if the pressure were low. But this thick nitrogen presses down. It holds those molecules as liquids. It keeps the lakes from instantly evaporating. It's like a lid on a pot, and this dense atmosphere also regulates temperature. It moderates the extremes. On a world with no air, the difference between day and night is huge. But Titan's blanket of gas smooths that out. It stores a little heat. It moves it around with wind. The result is a stable climate, very cold but stable. That long-term stability might be the most important thing when we think about life. Titan has kept this consistent environment for billions of years. A surface pressure that allows liquid lakes, a temperature that's cold but doesn't swing wildly. A chemical background of nitrogen that's reliable. This persistence offers time, a lot of time. If there is a pathway to some kind of cold biochemistry in those methane seas, it hasn't been interrupted. The stage has been set and kept set for an unimaginably long duration. It gives chemical systems the continuity they need to experiment, to build on small advances. Maybe to stumble towards something organized. In the search for life, we look for water and energy and organic compounds, but we also have to look for time. And stability. A world that can keep a consistent set of rules for billions of years gives chemistry a real chance. Titan's nitrogen sky is that promise of time. A stable blanket made from the pieces of its ancient past, holding in the cold and the quiet, guarding whatever slow experiment might be happening below. Dragonfly is still being built, but we're already getting a sharper look at Titan. The James Webb Space Telescope, that big infrared observatory, has been watching Saturn's largest moon. And the detail is, it's a step change. Webb sees in the infrared that lets it look through Titan's haze. Cassini gave us a broad map. Webb can pick out individual chemical signatures across the surface. It can watch gases in the atmosphere with real precision, track how methane and hydrogen cyanide move with the seasons. It can even start to map the surface composition. Tell the difference between pure water ice and areas covered in complex organics. This isn't just a better picture, it's a chemical census from 1,000,000 miles away. Each observation is strategic intelligence, gathered years before the Rotorcraft ever launches. Scientists will use this data to watch for sudden changes. A brightening over a dune field might mean a methane rainstorm. A shift in the chemistry near a lake shore could point to evaporation or seepage from below. Webb is a long-range scout, identifying the most dynamic places on Titan, the most chemically interesting spots, and that information will directly shape Dragonfly's mission. The flight plan isn't fixed. With Webb's updated maps, planners can adjust the drone's itinerary, maybe add a new waypoint to investigate a site that just became active. They can prioritize sampling areas that show the strongest signs of probiotic chemistry, so when Dragonfly finally touches down, it won't be exploring blind. It will arrive with the best possible understanding of its target, guided by the most powerful telescope we've ever built, and Webb is just the start. New giant ground-based telescopes are joining the watch, like the extremely large telescope in Chile, mirrors nearly the size of a basketball court. These instruments will be able to resolve surface features on Titan in incredible detail. From right here on Earth, they'll monitor the moon continuously, build a multi-year record of its weather and chemistry, right up to Dragonfly's arrival. This coordinated watch changes the waiting period. The years before launch aren't empty anymore. They're a time of intense, remote study. Each new observation sharpens the questions, turns vague mysteries into specific, testable hypotheses. By the time Dragonfly's rotors spin in Titan's thick air, we'll have already narrowed the search. We'll be sending a sophisticated detective to a crime scene we've surveyed from every angle, ready to examine the evidence we've only been able to glimpse from afar. The search on Titan isn't just about finding something new, it's about redefining what we're even looking for. For a long time, the idea of a habitable world was a simple picture. A rocky planet at the right distance from its star with liquid water on the surface, the Goldilocks zone, not too hot, not too cold. That was our map. And we used it to guide every telescope, every mission we sent out. But Titan, hanging there in the deep freeze 1 billion miles from the sun, shatters that map. It forces a deeper question. What does habitable really mean? Is it about a specific liquid like water, or is it about the fundamental principles that liquid provides? A stable solvent where molecules can meet, a source of energy to drive reactions, conditions that last over geologic time. Titan argues that these are the universal requirements. The liquid itself can be swapped, the energy source can be faint, the temperature can be brutally cold. If the core principles are met, solvent, energy, complexity, time, then a world earns the label habitable. This is a profound shift. It moves the goal from finding another Earth to recognizing the potential for life in any environment where chemistry can become persistent and complex and organized. Titan expands the habitable zone from a narrow orbital band into a vast spectrum of possibilities. It includes icy moons with oceans under the ice. It includes worlds with hydrocarbon seas under hazy skies. The universe's workshop for life might be far more diverse than we ever allowed ourselves to believe. More clever, really. This intellectual expansion is perhaps the most important gift Titan gives us. It prepares our minds. If we only search for life that looks like us, we are almost guaranteed to miss it. We could stare directly at an alien biosphere and dismiss it as interesting geology. By wrestling with Titan's cold chemistry, we are training our perception. We are learning to ask different questions. Not does it have water, but does it have a liquid that can act as a solvent? Not is it warm, but is there an energy gradient something could exploit? This philosophical shift is the prerequisite for any true discovery. It opens our eyes to the possibility that life might not be a single, rare phenomenon, but a common cosmic process, expressing itself in countless forms across a breathtaking range of environments. The journey to Titan, then, is also a journey inward. It challenges our assumptions, it stretches our definitions, and ultimately, it teaches us humility before the sheer inventive power of nature. The data from Titan is public. It belongs to everyone. When Cassini sent its last images, they didn't go into a private archive. They went online. Anyone could see them. And that changed things. It meant people weren't just watching, they could join in. An amateur with a telescope could log Titan's movement. They could add to the record. People took the raw mission pictures and processed them. They pulled out details, found colors. Sometimes they saw things the official teams hadn't. That's exploration now. It's shared. There are websites where anyone can help. You can look at pictures of another world and classify what you see. The human eye is still good at that. The Dragonfly mission is going to do the same. They'll release the data. They'll have tools so you can follow along. You'll see this drone flying over the dunes almost as it happens. It stops being a distant science project. It becomes a trip we're all on, and that matters. It connects to something basic, the question of whether we're alone. That's not just a science problem. It's a human story. It's the same feeling that makes you look up at the stars. These missions work because they turn the data into a story. The story of a probe going down through an orange sky. A nuclear-powered drone flying over alien sand. These are parts of our biggest adventure. They answer a curiosity you don't need a degree to have. It's a kid looking up and asking what's out there. That shared wonder is what fuels this. It's what gets a mission funded when it takes decades and costs billions. Public support makes the science possible. By sharing the data and the story, the scientists are inviting us in, to feel the awe of seeing a new world, to share the patience of waiting for a signal from a billion miles away. And maybe one day to share in understanding what it all means. Looking for life on Titan with all its technical details is really a human thing. It's us reaching into the dark and asking the universe a question. Together, the tools we build to reach another world end up changing ours. To send a spacecraft a billion miles and have it fly through an alien sky, you need a kind of creativity. That creativity doesn't stay in the lab. The challenges of Titan, the cold, the haze, they force engineers to solve problems in new ways, and those solutions spin off. They find new life. They improve how we live and work and heal right here. That's not a side effect. It's central to exploration. Trying to understand a distant moon becomes an engine for innovation on Earth. Take the core of the Dragonfly mission, autonomous flight. This rotorcraft can't be controlled from Earth. A command takes over an hour just to get there. By the time an engineer sees a problem, the drone has already lived with it for hours. So Dragonfly has to be intelligent. It has to navigate on its own. It uses sensors, LiDAR, cameras to map the terrain below. It finds a safe spot to land. It adjusts its flight path all by itself. It's making life or death decisions with no human in the loop. The software and algorithms for this are a leap in machine autonomy. And this isn't just for Titan. This applies to drones here. search and rescue drones that navigate collapsed buildings without GPS. Agricultural drones that map and treat individual plants in a field. The need to explore an alien world accelerates our use of robotics in complex environments everywhere. Then there's the environment itself. Titan's surface is nearly 300 degrees below zero. Electronics from a phone or laptop would shatter or fail in minutes. Building instruments to survive that cold for years pushes material science. Scientists develop new seals, new lubricants, circuit boards resilient to extreme temperature swings. These advances have immediate uses. They improve sensors for Arctic and Antarctic research. They lead to more reliable electronics for high-altitude aircraft, for satellites, for medical equipment in freezing storage. The drive to make something work on Titan makes our own technology more robust. Maybe the most profound spin-offs come from the analytical tools. Dragonfly carries a miniature chemistry lab, a mass spectrometer. It vaporizes samples of Titan's sand and ice to identify complex organic molecules. It has to do this with incredible precision, distinguishing thousands of compounds in one sample. The challenge of analyzing Titan's probiotic soup drives advances in portable, ultra-sensitive chemical analysis, and these improvements don't stay in space. They go into hospitals and labs. They lead to better tools for diagnosing illness, where detecting a single rare biomarker in a drop of blood can mean an early warning. They enhance environmental monitoring, letting us detect trace pollutants with greater accuracy. The machine built to search for alien life's building blocks could help doctors find the earliest signs of disease in a human body. This pattern repeats. Throughout space exploration, the need for miniaturized cameras gave us smartphone sensors. The quest for efficient solar power for satellites advanced renewable energy. The list is long. Investing in pure, curiosity-driven science, especially the extreme kind, acts as a catalyst. It focuses immense talent and resources on seemingly impossible problems. And in solving them, we don't just learn about Titan. We create a toolkit of new capabilities. These technologies then diffuse into the broader economy. They create new industries, improve old ones, save lives. The value of exploring a methane lake 1 billion miles away is measured in the data it returns and in the quieter stream of innovation that flows back into our world. Turning science fiction into tools for a better future. The idea of putting people on Titan feels like science fiction, but it makes you think on a different scale. To see that orange world not just as a target for probes, but as a place we might actually go. This is a vision for centuries from now. It only becomes possible if we get through our own problems here, and if we keep the desire to go out there. But just thinking about it is useful. It pushes what we imagine a human home could be and why we'd ever pick a place that alien. The potential benefits are as extreme as the environment. Titan has resources in unbelievable amounts. Its lakes and seas are actual oceans of methane and ethane. Those aren't just fuels, they're the raw materials for making plastics, chemicals, synthetic things. A base could use them to build structures, tools, even make breathable air through chemistry. The thick nitrogen atmosphere, though you can't breathe it, gives you a critical shield. It offers real protection from cosmic and solar radiation, which is a huge issue on the Moon or Mars. On Titan, you wouldn't have to bury your habitat under tons of dirt for safety. You could build on the surface under a dome with the sky itself acting as a natural radiation barrier. Then there's the science, which would be the first reason to go and the reason to stay. Picture a research station on the shore of Krakenmare. Scientists could go outside in suits, drill into the icy shore, and sample the liquid methane right there. They could watch the organic haze as it happens, follow the slow seasons, maybe even send submersibles down into the dark to look for signs of that slow, cold biochemistry. Studying a potential second origin of life right there on the spot would change everything. It would redefine our place in the universe, but the obstacles are huge, each one its own survival frontier. The cold is the most direct problem. At nearly 300 degrees below zero, any exposed equipment turns brittle, lubricants freeze, seals fail. A tear in a suit would be fatal immediately. The environment is toxic, not with poison but with a total chemical mismatch. The air is suffocating nitrogen with methane. There's no free oxygen. Every single breath would have to be made and carefully kept in. The distance might be the most isolating thing. A one-way radio signal takes more than an hour. A supply ship from Earth with current tech would take years to get there. A colony would have to be almost completely self-sufficient from the very start, a closed ecosystem in the deepest freeze. This long-term idea, even as speculation, changes how you see Titan. It moves it from something in a telescope to a place in a possible human future. It asks us to think of our civilization not as a thing on one planet, but as a process that could, with enough time and effort, learn to live in more than one kind of world. To look at Titan that way is the ultimate thought experiment. It tests our ambition against the reality of the cosmos, and it hints that the final point of going to a place like that might not just be to answer if we're alone, but to figure out what it would take for us to actually become neighbors in a universe full of strange and possible worlds. We know the lakes are methane and ethane, but the exact recipe that's still unknown. Is it a simple mix or a complex cocktail with dissolved nitrogen, benzene, other organics in the depths? That precise composition tells us about the moon's chemical history, the true nature of its solvent. On Earth, ocean salinity shapes life. Here, the makeup of the seas could define the chemistry within them. Then the dunes, those vast dark waves of organic sand. We've mapped their shapes, but what are they made of, grain by grain? Are they uniform, or do they hold layers? Different compounds, a stratified record of Titan's atmospheric history. Sampling them directly reveals the full inventory, the probiotic molecules this world manufactures. A catalog of ingredients available for more complex reactions. Cryovolcanism, that question is still open. We see the landscapes, the possible flow features. But is it active today? Does warm, slushy ice still ooze onto the surface, connecting the hidden water ocean to the hydrocarbon lakes, finding definitive proof, a fresh flow, an active vent? That would revolutionize our model. It shows a world exchanging materials between its two potential biospheres. A process that could accelerate surface chemistry beneath the ice shell, the subsurface ocean. Its own profound puzzles, the nature of the seafloor. Is it a smooth, cold plain, or is it geologically active, studded with hydrothermal vents like Earth's ocean floor? That interface between liquid water and the rocky core, it's the classic potential habitat in our solar system. Yet on Titan, it's the layer we understand the least. Does chemistry thrive there in the dark, powered by Saturn's tides? All these questions build toward the most pressing one. Are there chemical signatures that simply cannot be explained by non-living processes? Dragonfly's lab will scour the data for patterns that shout biology. A strong preference for molecules with one specific handedness. Skewed ratios of light to heavy carbon isotopes in complex organics. The mysterious depletion of hydrogen and acetylene right at the surface, concentrated in specific, likely places. Any of these would be a flare in the dark. A signal the complex chemistry has crossed a threshold into something organized. Acknowledging these unknowns isn't admitting defeat, it's mapping the frontier. For all Cassini and Huygens revealed, we are still just beginning, reading the first page of Titan's story. The most thrilling chapters, the ones that could change our understanding of life itself, are likely still ahead. Waiting in the data stream from a nuclear-powered drone, flying under an orange sky, the mission is built not to close the book, but to show us how much more there is to discover. The search for life on Titan, it's part of a much older story, a human story. We've always looked up and wondered if we're alone, if there are other minds out there thinking, feeling. That question has driven myth and philosophy, and now it drives science. And in that quest, Titan has become something special. It's not just another destination. It's a test case, a laboratory for an idea, that the universe might be more inventive with life than we thought, that the conditions for biology might not be a single narrow path but a broad highway. Many lanes. Our own planet gave us the only example we know, a warm, watery world, life built from carbon and water. For a long time, it seemed logical that other living worlds would look like ours. But Titan challenges that with its frozen lakes and organic snow. It asks us to run the experiment with different chemicals to see if the principles of life, self-organization, metabolism, can emerge from a completely different starting point. That's why Titan's place is so pivotal. Whether we find life in its dark seas or not, the result teaches us something. If we find it, we learn life is a robust force, capable of arising in environments we thought impossible. It would mean the universe is likely brimming with biology, in forms we're only beginning to imagine. If we don't find it, we learn something else. We learn about the boundaries, the specific conditions, the precise sequences that might be necessary to cross from chemistry to a living system. Titan becomes a benchmark, a data point that helps us calibrate our search across the galaxy. This perspective shifts the goal. The mission is no longer just about finding aliens. It's about understanding the cosmic recipe for complexity. Titan shows us a world can possess all the pieces: energy, liquid, organic building blocks, immense time, and still the final step might be elusive. Or it might be happening right now, in a slow, cold dance we haven't yet learned to see. Either outcome deepens our knowledge, it refines the questions we ask of the next world. Zooming out, Titan is a single chapter in an encyclopedia of worlds. Our own solar system, once thought simple, is now a collection of staggering diversity. Volcanic moons, ice giants, dwarf planets with hearts of rock, and Titan, with its layered mysteries, is a flagship for that variety. It stands as a reminder. If our own backyard holds such a strange and promising world, what must the galaxy contain? Around other stars, there will be planets with chemistries we haven't conceived. Environments that make Titan look tame. The quest Titan represents is just the beginning. It is training our eyes and our minds to recognize life not as a single phenomenon, but as a spectrum of possibilities. Each world we explore adds a new word to a vocabulary we are only just starting to speak, a language for understanding our place in a cosmos that is likely not empty but full of stories. Written in the slow, patient chemistry of countless distant shores, Titan is a story about perspective. You have to hold two things in your head at the same time. One is the distance. It's nearly 1 billion miles away, a world with silent lakes, organic snow, drifting in the dark on its own ancient rhythm, and the other is the connection. In its rivers, its rain, its chemical cycles, its layered oceans, you see a mirror of home, but it's a distorted mirror, built from methane, not water. That's the source of its power. It feels impossibly alien and also hauntingly familiar. That combination pulls at your curiosity. The journey doesn't end with answers. It ends with better questions. We started with a blurry orange dot. Now we know it as a place, vast hydrocarbon seas, dunes of frozen organics, a hidden water ocean that might whisper about a second kind of habitability. We've traced the slow dance of its methane cycle, watched the chemical factory in its sky make the building blocks of life, imagined a biology that breathes hydrogen and drinks liquid natural gas. Every discovery expands what a living world could be. Dragonfly is the next logical step. It turns remote observation into direct exploration. This nuclear-powered drone will be our eyes and hands on that surface, tasting the chemistry of the dunes, the ancient impact craters, searching for the subtle fingerprints only a living process could leave. Its journey writes the next chapter. It could confirm our boldest speculations, or it could reveal pathways to complexity we haven't even dreamed of. It's worth remembering the true scale of this. The search for life on Titan or anywhere, it's not just a hunt for another version of us. It's a fundamental exploration of the universe's creative potential. We're trying to learn the rules of a cosmic game where we've only ever seen one player. Finding life built on a different chemistry would tell us the game is far bigger. With many more ways to play, not finding it would teach us how precious, how precise the conditions for a living world might be. Both outcomes are profound. So you look back at that hazy orange moon, now seen with new understanding. It stands as a beacon. The universe is a place of endless variation, of quiet wonder. The mysteries of Titan invite you to keep questioning, to keep exploring, to hold onto a sense of awe before the vast, intricate tapestry of nature.